In this class also we are doing the problems on first law of thermodynamics and isothermal and adiabatic expansions, mostly isothermal expansion and first law of thermodynamics. So now let's do the first problem, that is problem 1. Determine the work done. Determine the work done in the expansion of a gas from 10 liters to 20 liters against 1 atmosphere external pressure. Here we may get a doubt whether it is a reversible process or irreversible process. Whenever we have external pressure, fixed external pressure, that is irreversible process. But in reversible process, generally there will be no constant external pressure. The driving force is slight difference between the internal pressure and external pressure. So here there is a fixed internal external pressure, therefore it is a irreversible process. Okay, so keep that aside. Now we are dealing this problem. What is the work done for the expansion? Now let's use the work expansion. Work equal to negative P delta V. And what is the pressure? External pressure here is, remember this is external pressure, therefore P external given in the problem as 1 atmosphere. Now here the gas is expanding from 10 liters to a final volume of 20 liters. Therefore, I can write V1 as 10 liters, V2 as 20 liters. Now, what is the delta V? Delta V is equal to V2 minus V1. That's equal to 20 liters minus 10 liters. That gives us 10 liters. Now, if we substitute that in the work expression, then W is equal to P external. So what is the P external? That is 1 atmosphere times, what is the delta V? We have just now calculated delta V as 10 liters. That gives us the work is equal to negative 10 liter atmospheres. And what is the negative indicating here? The negative is indicating that work done by the system. How can we say work done by the system? Is an expansion. Expansion is from the work coming from the system by the gas. So this is a liter atmospheres, which is a unit of energy. And if we want to convert that into joules and kilocalories, we need a conversion factor. What is the conversion factor? 1 liter atmospheres is equal to 101.3 joules. At the same time, 1 liter atmosphere is equal to 24.2 calories. Now let's substitute that in this expression. So W is equal to negative 10 liter atmospheres. Now I can multiply this with the conversion factor. So 101.3 joules divided by 1 liter atmospheres. That gives us 1013 joules of work, which is negative, means expansion work. The same thing if we express in the calories, that is negative 10 liter atmospheres times 24.2 calories divided by 1 liter atmospheres. That gives us 242 calories of work done in this expansion. So that is the first problem. Now let's go to the second problem. Remember, the first problem is actually expansion. Expansion is done at the expense of system energy. That's why we always have work done by the system as a negative side. So as such, work is not negative. Work, energy, all those are positive numbers only. But to indicate the direction of the work, we use the sign convention from the system's point of view. Now let's go for the second problem. What is the second problem here? The problem is What is the work done when a gas absorbs 800 calories and calories heat and loses its internal energy 200 calories. So here the work done by the system by taking the heat and from its internal energy also. So here clearly, clearly the first law of thermodynamics will be useful in solving this problem. What is the first law of thermodynamics? That is delta E is equal to Q plus W. This is the simplest form of the first law of thermodynamics. But here the crucial point is we have to decide the sign convention. So in which direction the energy is flowing. That means is it flowing into the system, is flowing out of the system. Now let's say the keywords. What are the keywords here? Gas absorbing the heat. That means Q is positive 800 calories. Now there is a change in internal energy. The change in internal energy is given as loss for the system. Therefore, we should take delta E as negative 200. So, if we substitute these numbers in this problem, so delta E is negative 200 calories equal to what is the heat here? Is 800 calories, which is positive, plus W. So from this we can get W is equal to negative 200 calories minus 800 calories. That gives negative 1000 calories of the work done by the gas in this expansion. How? 200 calories of work done from its own energy and remaining 800 calories of work done from the heat it has absorbed in the process. So here the work is done from two factors. One is the heat the system is absorbing, which is gas, and also the own energy of the gas, 200 calories, that is also useful in carrying out this work. So in total here we are extracting the 1000 calories of work. Okay, now let's expand this into the joules, and we know that W equal to how much we got here? Uh, negative 1000 calories. And what is the relationship between calories and joules? And we know that 1 calorie is equal to 4.184 joules. Now, if we substitute here, the work done in this process in joules is negative 1000 calories times 1 calorie of work generally is equivalent to 4.184 joules. That gives 4184 joules. Am I correct in the mathematics? Let me check with the calculator. 1000 times 4.184, that is 4184 joules of the work done. So work done by the system, that is indicated by the negative sign. So this is the second problem where work is done by both heat and also from the internal energy of the system, which is gas in this case. Now let's go to the third problem. What is the third problem here? Third problem is find the change in internal energy. Find the change in internal energy when a gas expands from 20 liters to from 10 liters to 20 liters against 2 atmospheres external pressure and absorbs 100 calories of heat. Okay, here expansion is done in in two ways. One is taking the heat. What is the other way? Maybe using its internal energy or may not be. So if the 100 calories is enough to carry out this expansion, it doesn't use its internal energy. If it is the more work happening in this expansion from 10 liters to 20 liters, then more than that 100 calories extra energy must be used from the internal energy of the gas. Okay, now what is the formula here? Again, the same formula. What is that? First law of thermodynamics. Delta E is equal to Q plus W. Okay, now here the heat is absorbed by system, therefore the sign of the Q is positive, 100 calories, and we don't know what is the sign of the work, and we should search for the keyword. What is the keyword? Expansion. The expansion keyword indicates that the work is a negative term. Okay, therefore let's find out what is the work here. Negative P delta V. So that is, what is the external pressure? That is negative 2 atmospheres times, what is the change in volume? Final volume is 20 liters, initial volume is 10 liters. So from that we can say that delta V is 10 liters. That is 20 liters minus 10 liters. So that gives negative 2 atmospheres times 10 liters. That gives negative 20 liter atmospheres. So there is a problem here. The heat is actually given in calories, whereas this one is in liter atmospheres. Therefore, we should make both of the units into the same same units. So therefore, I convert the work into calories. So that is negative 20 liter atmospheres, and we know that 1 liter atmosphere is equal to 24.2 calories. So that gives us negative 48.4 calories of work done by the system. Now let's find out what is the internal energy system by substituting the heat and work values in the first law of thermodynamics, which is delta E equal to Q plus W. So that gives us delta E equal to Q. We know that that is 100 calories plus work. What is the work we got? Negative 48.4. So am I correct in the maths? There is some doubt. 20 times 22, 24.2, that is 400. Very pure mathematics. That is 484. Very sorry here. So 484. So let's substitute these two. So the heat factor is 100 calories, whereas the work factor is negative 484 calories. Therefore, delta E is equal to negative 384 calories. What is the meaning here? The expansion work of 484 calories is coming from 100 calories of heat, and remaining 384 calories of work is coming at the cost of internal energy of the gas. That is why there is a drop in the internal energy of the gas by 384 calories. So that's the important thing here. System can take the heat, convert that into work, and sometimes it can take the heat and do the work. It also uses its own energy to do the work. And what is the third way? It doesn't take any heat. It only uses its own internal energy and performs the works. Three ways we can extract work from any system. Now that's how things work in thermodynamics or in general life. Now let's go for next problem. A gas expanded at expanded at a constant pressure from 100 Kelvin to 200 Kelvin. Determine the work done for 1 mole of gas. 1 mole gas expansion. So in this experiment, the gas used is only 1 mole. So here there is some problem. So we don't see any volume words here. So we see the change in temperatures, and there is a moles, and there is no CPC was given. And we need to find out the work here. What is the work expansion? Work is equal to negative P external times delta V. Okay, here we don't have a delta V term basically. So we need to have another form of expression for the work here. So now let's take, so we know for the ideal gas equation PV equal to RT. Why? Because it is a 1 mole. For n moles, that is PV equal to nRT. So PV equal to RT is the equation of 1 mole of ideal gas. So here the volume change is accompanied when the temperature changes, and he says the pressure is constant here. Therefore pressure is a constant term. The volume change results from temperature change. So the two parameters here are temperature and volume. Therefore if we do the math, the differentiation, that gives P delta V is equal to R delta T. And the same thing, if we substitute here, we get expression for the work as negative R delta T. What is the negative sign indicates? The negative sign indicates work done by the system, which is expansion. That's equal to, let's use the R value. We can use the calories or we can use the joules. It is our choice. Now let's go for the joules. That is negative 8.314 times, what is the joule temperature change here? 100 Kelvin to 200 Kelvin, and the change in temperature is 200 minus 100, which is 100 Kelvin. That gives you negative 831.4 joules. Kelvin mole here is unit. So we get, this is the expansion work done when 1 mole of gas expands at a constant pressure and 100 Kelvin to 200 Kelvin. Temperature is increasing in the process. There is something wrong in this problem. 100 Kelvin temperature is rising. Expansion is happening. Temperature is rising. This is a work done actually. Maybe the temperature rise is due to some additional heat coming from outside to the system. We don't know how it is, but this is a problem. This problem, the work done is 831.4 joules per mole of the substance. Okay, but still the temperature is increasing. The temperature increase is not because of the expansion, it is because of something else. So this is the very typical problem here. It may confuse us, but when the system doesn't absorb any heat from outside, there will be fall in temperature generally when the expansion happens. Okay, now let's go to the next problem. The next problem is this one. Find the work in joules when 3 mole of an ideal gas at 27 degrees centigrade expands isothermally and reversibly from 1.013 times 10 raised to the power of 6 Newton meter power negative 2 to 1.013 times 10 raised to the power of 5 Newton meter power negative 2. So this is the problem. Here in this problem, the gas used is 3 moles, a temperature of 27 degrees centigrade and reversible. So the temperature is 27 degrees centigrade. Here there is no clear mention of any constant pressure. So reversible process, that is how it happens. There will be very little difference between the system and surroundings. There is always equilibrium existing between them. Work happens slowly. So initial pressure is P1 is equal to 1.013 times 10 raised to the power of 6 Newton meter power minus 2. And what is the final pressure is P2 is equal to 1.013 times 10 raised to the power of 5 Newtons meter power minus 2. So here we need to find out the work done in expansion for 3 moles of gas isothermally and which happened in a reversible manner. What is the formula for work done in reversible isothermal expansion? That is negative 2.303 nRT log. If we use the volume terms, that is V2 divided by V1. But here in this problem, we do not have a volume terms, we have a pressure terms. Therefore, we should use P1 over P2. So we know N equal to 3, and what we are substituting for R decides in which units we are expressing the work, and temperature is we must express always in kelvins. So pressure we can use any one. Okay, now let's go for but the problem is in joules. So therefore we must use R value as 8.314 only. So therefore let's substitute the values. The work is equal to negative 2.303. Now how many moles of the gas we are using? 3 moles, and R value is 8.314, and temperature 27 degrees centigrade means 300 Kelvin times log, and what is the initial pressure? That is 1.013 times 10 raised to the power of 6 divided by 1.013 times 10 raised to the power of negative 5, sorry, 10 raised to the power of 5. So if we do the mathematics, let me use the calculator. Let's, without doing the calculator, we can use it. So this is 10 power 6, 10 power 5. So we get 10, log 10 is 1, and we are only left with 2.303, 3, 8.314 and 300. So if we do the mathematics of that one, 2.303 times 3 times 8.314 times 300. So I got negative 17,232.4 joules of energy. This is the work done by the system at constant pressure, sorry, at constant temperature. So how? When the system is at constant pressure, it doesn't use its internal energy. Its internal energy doesn't change. But how the system is able to perform the work? It absorbs heat from other source, and uses that heat to do the expansion work. So therefore, this is the isothermal expansion where heat is used to perform the work. Now, let's go to the next problem, which is last problem of the class. So that is very difficult to memorize the problems. Find the work of expansion when 3 mole of an ideal gas initially at initially at 1.013 times 10 raised to the power of 6 newtons meter power minus 2 and 27 degrees centigrade, expands isothermally against constant external pressure of 1.013 times 10 raised to the power of 5 Newton times meter power minus 2. This is a very nice problem. It looks similar to the previous problem where the 1.013 times 10 power 6 and another pressure is 1.013 times 10 power 5. The numbers look same when we compare with the first problem. But there is a hint here. The problem which we have done in the previous case was actually a reversible expansion. But here it is not reversible expansion. How do we recognize whether a process is reversible or irreversible? In irreversible process, expansion happens against a constant pressure. Whereas in the reversible expansion, the system pressure and external pressure are always same. Very slight difference. So here the catch point is constant external pressure indicates this is an irreversible process. Therefore, here what is the formula we are going to use? Certainly, we are not going to use the formula negative 2.303 times 10 raised to the negative 2.303 nRT log V2 by V1. We don't use that formula. Which formula we are going to use? We are going to use the formula W equal to negative P delta V. Okay, there is another doubt. Where are the volume terms here? And we need to find out the volume terms. So V1 and V2. How? We can use the ideal gas equation. What is ideal gas equation? PV equal to nRT. To find out the volume, the formula is V equal to nRT over P. So here we have two conditions, two states, initial state and final state. So what is the initial volume? V1 is equal to 3 moles of the gas and R value, let's take in liters, that we should take 0.0821 times temperature, that is 27 degrees centigrade, that means 300 divided by what is the pressure, 1.013 times 10 raised to the power of 6. So what does it give us? It gives us some number. Okay, let's keep this number. Now what is the other number we have? Other one, V2 is equal to same 3 moles, 0.0821, and here what is the final temperature? It's an isothermal process. There is no change in temperature, that is 300 again divided by, and what is the final pressure? The final pressure is expansion happens till the internal pressure is equal to the final pressure. That's going to be 1.013 times 10 raised to the power of 5. So this is the V2. So therefore what we need to find out? We need to find out V1. If we do the mathematics, let me do the mathematics. So that's going to be 3 times 0.0821 times 300. So that gives so did I substitute the actual units of R? What are the units of the pressure here? The pressure units are SI units. Therefore, we must find SI units of the R. So that is basically 8.314. So let's use 8.314 here. So that is 8.314, 8.314. So what are we going to get? Let's see the maths now. 3 times 8.314 times 300 divided by 1.013. So I got 7386.6 times 10 raised to the power of negative 6. And what about the final value? So let me do the math again. That is 3 times 8.314 times 300 divided by 1.013. I got 7386 point, oh, 10 raised to the power of 5, that is 7386.6 times 10 raised to the power of negative 5. So these are the values. Okay, now let's do the work done. So that is work equal to negative P external. What is the P external? We already know that is negative 1.013 times 10 raised to the power of 5. And we have, uh, let's go to that one, 10 raised to the power of negative 6. 7386.6 times 10 power negative 6. Other one is 7386.6 times 10 raised to the power of negative 5. So here the confusing units. So what are the units? Here we get meter cube, but we should convert them into uh, liters. How do we do that? Okay, let's substitute here. So let's take the liters. 7386.6 times 10 raised to the power of negative 6. So here we get meter cube. So which is not a good unit to do the problems. We must convert that into uh, decimeter cube, which is liters. And how do we do that? Let's do that. Okay, so meter cube to decimeter cube, and we know 1 decimeter is equal to 0.1 meters. So that means, so this is going to be, so okay, from this I can say 1 meter equal to 10 decimeters. 1 meter cube is equal to 10 power 3 decimeter cube. So it gives us 7386.6 times 10 raised to the power of negative 6 times 10 raised to the power of 3 decimeter cube. So we will end up with 7836.6 times 10 raised to the power of negative 3 meter cube. So that will be simply 7 point, why did I get 7836? Sorry, something wrong again. This is 7386. 7386, 7386. That gives us 7.386 decimeter cube, which is equal to liters, 7.386 liters. Now final value. So how do we get the final value? Same thing. So we should take 7386.6 times 10 raised to the power of negative 5 meter cube. So that's going to be 7386.6 times 10 raised to the power of negative 5 times 10 power 3 meter decimeter cube. So that will give us 7386.6 times 10 raised to the power of negative 2 decimeter cube. So this is, if we write in a scientific notation, that is 7.386 times 10 raised to the power of 3, and this is 10 raised to the power of negative 2. So that will end up with 10 raised to the power of 1 times 7.386. So we end up with 73.866 decimeter cube. So which is equal to 73.866 liters. So we got final value as 73.866. This is V2, and V1 is 7.386. Now let's substitute here. What is the final value we got? 73.866 minus 7.386, and this is atmospheres, sorry, this is newtons times meter power minus 2, and this is liters. So we will end up now with negative 1.013 times 10 raised to the power of 5. And what is the difference between these two? 73.866 minus 7.3866. So I got 66.479. 66.479. So that will give us, so 67.34 times 10 raised to the power of 5. So that is Newton times meter power minus 2, and that is liters, but we should convert that into joules. So what is the joules unit? 1 joule is equal to, so let me erase this mass here a little bit. So this one has the units of negative 67.34 times 10 power 5. So Newton times okay, let's do the mass here. Newton times meter power minus 2, and other one is decimeter cube. So let's make this into liters. Newton meters, which is joules, 67.34 times 10 raised to the power of 5, and this is a Newton meter power minus 2. This is decimeter cube. So if we convert that into meter cubes, that will give us 10 power minus 3 meter cube. So that will end up with, this is 10 power 5, 10 power minus 3. That will give us 10 power 2. That gives negative 67.34 times 10 power 2 Newton meters. 10 power 2 means 100. 67.34 times 100 is 6700. Okay, let I am worrying in maths little bit. 67.34 times 100. I get 6734 Newton meters. So that means basically this is 6734 joules of the work. Why did I say it is joules? Newton meters is equal to 1 joule. So this is the answer. The work done in this expansion. How much is that? 6734 joules of expansion work done in this irreversible process for the same kind of problem that we have discussed previously, which was a reversible expansion. There the work done is 17,232, but here the work done is only 6,734. So what it clearly indicates, work done in reversible process is always higher than work done in irreversible process. But what is the problem with the reversible process? Reversible process happens very slowly. That is the disadvantage with the reversible process, and that is the advantage with the irreversible expansion. What is the advantage? That is, it happens quickly. So these are the problems of first law thermodynamics and expansion in isothermal process. In the next class, we are going to handle Joule-Thomson effect. Thank you very much.